Welcome everyone. Thanks to Sujit for volunteering to take us to the next lecture day. Take it away, Sujit.
All right. So basically, I wanted to just say one thing here. You know how Jeremy Howard basically, does half lectures from different areas. And he keeps on. I guess it's a teaching tactic so that you can have people, kind of coming back in for the next lecture. But what I was going to do is I was going to take the entire matrix multiplication and run this through, in one shot, right, today. So there were things that I have ignored. So there was in this lecture, Jeremy Howard did like a very high overview of a diff-edit paper. So I'm going to skip that and push that to the next session. And he also talked about why recreating the embeddings, going from clip embeddings to clip or input text is not really, there is a place which claims to do that, and he says he kind of deconstructs that, and he says it's not really, what they are doing. So I'm going to skip that part for today and keep it for the next one. And where we also do the mean shift clustering algorithm, right? So that's a smaller piece. So, hopefully we can fit everything together in that. So today we'll just go with matrix multiplication, and I will share my screen. Yeah. So, okay. So basically the idea here is that he wants us to do matrix multiplication from foundations, and the idea is that you're using plain Python to start with, and as you implement each piece, you are then allowed to use what you will use finally, right, what you would use in regular application code. So see, these are all the like prerequisites he wants, so that about a little bit about Python, a little bit about Python modules and so forth. And FastAI datasets is kind of no longer needed. This notebook has nothing to do with FastAI, right? Or no connections to the FastAI API. And
Sujit, could you make the font a bit larger?
Okay, all right. Is this good, or should I go further?
Yeah, this is good.
Okay, cool. All right. So, and this is the source notebook, which I copied the code from and basically ran it on my own. There is hardly any difference except for a few, small annotations that I have built in just to, to explain, to you guys, right, for my use. So here's an animation. So essentially, before we go into matrix multiplication, and I know that most of you probably know this already, but what is matrix multiplication, right? So if you have like two matrices, for instance, like these, so this is like a 2 rows and 2 columns, so it's a 2 by 2, and this is a 2 rows and 3 columns, so it's a 2 by 3 matrix. So you're multiplying a 2 by 2 matrix with a 2 by 3 matrix, and ultimately you expect to see a 2 by 3, right? Because the inner part is 2, so 2 by 2 and then 2 by 3, so you end up with a 2 by 3. And if you look at this, essentially what it is doing, it's taking the first row and the first column, multiplying them element-wise and adding it and summing them, right? And it's doing that for each row and each column, so each row of matrix, the left-hand side matrix, with each column of the right-hand side matrix. And this is basically how it does it. And, yeah, it's really, really simple. But that's what we are going to implement in the notebook. All right, let it finish. Okay, okay. All right, so I'm going to go back here. Yeah. And so this is actually not even needed, I think, because we're not using internal libraries, but we'll keep it here. And matplotlib inline is kind of implicit, but we'll keep it here as well. This was an original notebook. I put all the exports in one place. So, and there are some inlines as well, but these are the main ones that we are going to use. So the exports are here. We are going to work on the MNIST data set. So the matrices that we are going to work with are basically, they represent MNIST images, which are 28 by 28 by 1, grayscale images, representing handwritten digits, right? Each panel of 28 by 28 by 1 is that represents one handwritten digit from 0 to 9. And these are available here in this gzip file. So essentially you're downloading it here, right? You're creating a path and you're downloading it here. And so here is something that Jeremy kind of gives you advice on, and so he basically tells you that almost all of PyDocs is available on the web, right? So not almost all of PyDocs is available on the web. And so for instance, if you were looking for the docs for URL retrieve, you could then just click something like this. Basically Google for URL retrieve, you'll find it. And then you will have very, very detailed description of how to use it and so forth, right? So this is just a pointer to kind of use this. So, actually, let me also start hitting these guys. So, actually, let me clean it up first. Change. Oh, also, because we are finally going to use CUDA, so I have set it to use GPU, right? This is something, the later few cells will use the CUDA with number, right? So that's why you need to have GPU set up, right? So any case, let me clean up everything. Interrupt, restart, runtime. Okay. All right. So then I'm going to start, hitting these cells so that we actually run it through. So here, it's creating a directory, right? So you can see it just created this data directory here, and then it downloaded the PKL, the pickle zip, right? And you can see it from here as well, right? And then it's basically reading the zip file using gzip open, and doing a pickle load and outputting the outputs. The outputs are basically a three tuple of two tuples, right? So these are pairs, and there are three of these. You don't want the test split here for purposes, so we are just getting the train split and the valid split. And this is the X, right? The actual images, and these are the Y's are basically says that this handwritten digit is a 1 or a 2 or a 9 or whatever, right? So anyway, so let's so he basically does this now. Opens it. Now you'll have these X train, Y train. These things are in memory, and you can interrogate them, right? So you can say that what is the length. So these are lists, right? As we could see, like these are tuples, so in kind of list, and the length of them is the X train has 50,000 of the X values, and so basically X train has 50,000 records, and the X valid or the valid split has 10,000 records, right? And the type of these are arrays, right? Not lists, sorry. These are NumPy arrays, basically two-dimensional arrays. And if you look at the shape of these arrays, you will see that these are of size, 50,000 rows, each with 784 columns. And 784 is because it's 28 by 28 by 1. So if you flatten it out, it's 784, right? And similarly with the Y train, these are the labels. So there are 50,000 of them. And similarly with X valid and Y valid, the 10,000 and 10,000, right? Okay. So our objective here is to basically start with Python, right? So Python doesn't have, NumPy is not part of Python, right? So we want to basically bring it down to lists. So what we do here, we take the first element of the first image, right? Sorry, we take the first image here, right, of X train. So first element of X train, And then we, wrap it in a list, which basically makes it a list, right? And we know that, this is, if you look at this one, so first element is basically, 784 or just 784, right? So this is going to be a list of 784 floating point elements. So they're basically grayscale from 0 to 1, right? So 0 meaning absolute black, and 1 meaning absolute white, and gray in, all the numbers in between, right? So, and then you take the list of that, and because most numbers, handwritten numbers will have a lot of dark around the edges, we basically choose like a spot somewhere in the middle, right? So, we take a slice of 200 to 210, and then we see what the values are, right? And you can see that there's some zeros and there's some, grayscale stuff, and this is almost white, and this is kind of, in the middle or towards the black end, right? So any case, so this is, what you have inside, right? Just to peek at what you have inside. So then he goes into a sidebar of how to use, generators and yield and so forth. And he talks about the iter function, right? There is quite a lot here. So, there is, nice, descriptions here on how to use generators and so forth. But really, the thing to note here is that this is a function, right? And this function, unlike regular functions which, return something using the return, right? This returns, it's kind of returning, but it's yielding to you, right? So how you call it is basically as if you call the chunks and you say, okay, so in this case, you have 784 of these things, right? So len x, you have passed the vals here. So sorry, vals here is 10, right? So you got 10 of these guys, 10 elements, 200 to 210. So you're passing in vals and you're saying, give me chunks of 5. So essentially what you're doing here is that you're, creating a chunk from, 0 to 5. And then you're saying you're, basically you're yielding. So the first chunk that you gave is like 0 to 5. Then the second one is 6 to 10, 5 to 10, actually. Sorry, 5 to 10, 0 to 5. Yeah. So 5 to 10, or 6 to 10, sorry, 6 to 10. So essentially, the idea is that each time you call this function, it will give you one more, right? And because you have it in a for loop, it's yielding each time. So it's giving you, so if you do a chunk vals, it'll give you an iterable object of, 2 of these arrays, right? So this array and this array, right? Sorry, this array. So it's giving you like that, and you wrap it in a list, because otherwise iterable elements are not viewable. So if you don't have a list, it will just show you it's an iter element, right? There's not. So, and this will actually, what's that called? Materialize it. List, wrapping it in the list will materialize it. So, and as you can see is now, if you just extend this and you say, instead of, giving me chunks of 5, take this image, this, long list of 784, and you give it to me in chunks of 28, right? So each row is 28. So essentially you're returning a list of, list of elements, and the inner list is 28 size, right? Rectangular inner. So essentially it's almost like a matrix, but it's basically an outer list containing a list, each list of which represents a row in this element, in this image, right? So you're basically calling the same thing, and you're wrapping it in I'm sure in order to see it, right? So if you do this, okay, let me see, what did I do? Okay, sorry. So I have to run this, and then I have to run this, right? So this was the function definition, right? So I had to get this thing. So essentially, as you can see here, this you're getting back the entire matrix from what used to be like a flat list of floats, right? You're getting back this entire image, right? So our iter and yield is basically working, right? And you can also do the same thing with instead of writing this thing here, this yield xii plus size, you can also use islice, which would actually take an iterable and slice it. So here you're saying that, wrap this, you had vals here. Vals was this list of 10 floating point elements. And you're basically saying that, wrap it in an iter function. So which gives you an iterable on top of the list, so which is again, and then run an islice on top of the iterable, right? And islice, each slice would be of length 5. And you can see that, this is what it gives you. And you can, and the idea here is to, to look at yield. So if you look at the first slice, this is what you get. The second slice, you get this, right? If you remember, these are the same arrays that we got here, right? These are the same, these are the same lists that we got here, right? And if you do one more, so I can do one more here, you should get an empty, right? So this is basically, there's nothing more in this iterable, right? So you have iterated through the iterable, all of it, because it was 10, right? So the first one was 5, second one was 5. Okay. So again, you can do the same thing that you did here, but using this new islice idea, right? And if you do that, you see, not surprisingly, you get the same result. And here he's using, so he's basically, so as you can see here, this one was operating one row at a time. So in order to make it operate on all rows, he's wrapped it in a lambda here, right? He's using a lambda here. I don't think he was using a lambda there, but I'm not sure. Yeah, so he wasn't using a lambda there. So in this case, he's using a lambda to basically. So another thing that, in case you're not familiar with lambda, is something maybe to look it up and see how lambda is set up. But most people are, so we will not go there. Okay. So now the second thing that he talks about is that the way in which you access an element of the, this list. So in order to get, say, if you look at this one, the image 2015, right? So this is the 20th row here. So maybe here and 15th, right? So somewhere along this area, right? You want to know what the grayscale value is here. The intensity is here. So to do that, you would have to, because it's a flat list, because it's a list of lists, right now with image. So you would have to call it like this, right? So you first get the 20th row, and within that, you get the 15th column, right? Zero based, of course, right? So, and then you get this. So great. I mean, this is a way to do it. But when you're talking about things like this, like matrix kind of things, you really expect to say image 20, 15, right? So, but this is not supported in the list abstraction. So he creates this new abstraction called matrix, which is a class. And he has this, so these are the init, the, underscore, init, underscore. These are called dunder methods. And these, and these are like special presets almost, right? So, you can think of these as like if you're coming in from an object-oriented background, so you can think of this as the, prototypical object from which everything inherits, right? And these are functions that have specific meaning in that context. So get item basically, if whatever you pass in here in this ID access, right? This will return. It's almost like a lookup element, right? So if you look at a dictionary, for instance, like you have dictionary, and then you say okay key, and it gives you the value associated with it. Or if you look at a list and you put in an index, and it gives you the value at that index, right? So those are all implementations of get item. So similarly, so here he's created a matrix object which inherits from the prototypical object, right? It's implicit here. And this is the constructor in it. And so in the constructor, you're basically passing in the list of lists that you have, right? So it's got it here. And then you define this get item, which tells you how to find an element in this matrix object, right? So, and then in the ID access is basically you have to pass in like a tuple, right? So it's like say 20, 15 that you pass in here. And then, so internally what you're doing is exactly this thing, right? So you're saying image 2015. Here you're saying self access IDX is 0, the first element of this thing, and you put it in square brackets, and then from that object you are pulling out IDX1, right? And so if you now do this, right, you create a matrix and you basically say that, okay, give me 2015. You'll find that they're identical. Again, not surprisingly, but this is kind of the abstraction in which he goes to. So according to our rules, now that we know how to extract things from a matrix, so we are now allowed to use the torch tensor abstraction. So these are kind of strange rules he makes as he goes along, but this is one of the rules here. So here you have to so you can basically use torch tensor, and if you pass a list to the torch tensor constructor, you get back a tensor, right? It's a torch, again, like matrix, it's an abstraction, but from the torch library. And so here you want to now convert the X train, Y train, X valid, Y valid that we got, which were basically flat lists, right? Of of size 50,000 and 10,000, flat lists of 784 numbers. So you want to convert those into torch tensors, right? Both X and Y. So to do that, you basically pass it through a map higher order function, and which takes a lambda. And so internally, if you look at the one that he had, let's see. So this is the one I copied from. Okay, so torch tensor, let's see. Or maybe just tensor used. Okay, maybe use for the, okay, here it is. So here, what he's doing is he is basically calling map tensor, right? Without the lambda, which is, the lambda is implicit here. The first element is a function that you pass in. So here, though, because I'm passing in this function with parameters. So what happened with me is that maybe I'm using a different version of torch, or maybe my parameters are set otherwise, my global parameters. But when I do tensor, these, if you remember, these things, so these things, you already saw floating point numbers in there, are numpy arrays of type float, right? And when I just pass it in using tensor, it basically converted to type 8, right? So I had to basically explicitly specify torch float 32 here. The other way to do it is that you can use torch from numpy, right? Which is a simple way to do it, and you don't have to pass any parameters. It keeps the type, right? The element type. So in any case, this is the only difference I had to make. So I had to, because I had to pass in parameters, I put in a lambda. Otherwise, everything is the same, right? So you basically pass it into a tensor. So lambda x is what you are, pulling from each of these things. And and then because these are X trains, so for each of these are all rectangular lists of lists, right? And so you basically pass it into a tensor, and that creates, internal tensors and of type float. So let's do that. And then we can look at the shape. If you call shape on it, now you will see that these are torch size, right? So they're basically torch objects now. And it is giving you, when you ask for the shape, it's actually giving you the size object with 50,784, 50,000, 10,074, and 7,000. Okay, all right. And if you look at the type, again, no surprise, it's a torch tensor, right? Okay. So again, let's look at it as the image. To do that,
that's why you have passed the D type there.
Yes, to keep it, keep the as a float. And I can show you actually. In fact, let me do one. Then maybe we can code. Okay. So if I do say map tensor, and then maybe just say X train, right? X train. Oh, sorry. Okay. So let's see.
To list it to
I
get
think
the
you have to
whole
list
thing
it.
or choose a slice.
So yeah, thank you. So as you can see here, these are okay. Actually, maybe take. Actually, this may not be. I may be wrong here. Maybe I did not actually need to do it. Okay, let's take maybe say 200. 0 maybe. Yeah, these are float.
It won't work for me, Sujit.
I think it does work. Sorry, I may have overreacted. So we can basically, you don't need this, right? So okay. Yeah, I saw ones and zeros, I think, in the edges, and that's where I freaked out. So I maybe have, yeah, you probably don't need it. You can basically use this formulation here if you want, right? Using map, but this is also a valid way to do it. So explicitly specifying doesn't really hurt. But in any case, so but as you can see here, the torch size here is still flat, right? So it's 50,000 of these images, each of size 784. In order to give it to, to pass it to an image, right? Or basically for plotting purposes, you need to basically reshape it to like a three-dimensional thing, where the first is a channel. So you have one channel, it's a grayscale object, and it's a square image of size 28 by 28. So you basically reshape this, so you take this, and this -1 basically says that, you basically break it up in a 28 by 28 and then just push everything backward, right? So in this case, your X train is of size 50,000 and 784. So you have already taken 28 by 28, which takes care of the 784, and -1 means that, whatever's left in my thing, just reshape it up that way. So essentially what you have got here is an array of 50,000, 28, 28, right? So from 50,784, you became 50,000, 28, 28 using reshape. And so now you can look at the 2015 area that we have been looking at earlier, right? The 0.984 or whatever. So now you can see it's 0.9883. And I think it's just, yeah. So if you look at 0.9882815, and now it's 9883, right? So it's just a, okay. Did I actually hit this? Maybe I didn't. Let me just do it, just in case. Okay, so it's 0.9883. Okay. And then if I look at image 0, again, no surprises. It's but this is using a tensor object, and yeah. So the other thing, this is again another sidebar that Jeremy Hort goes into. He talks about using unit tests in your Jupyter notebook. So as you progress, you basically take these elements and you say, okay, basically make assertions. He doesn't actually use the word assert, but I like assert, so I put it in here. And I think assert is more explicit in that sense. You can basically just run these by itself. You can have individual cells, but here you can group multiple assertions in one cell, and if one of them fail, the cell fails, right? So so here I'm basically saying that image 2015, this is my list object, is the same as the IMGAS, which is the tensor Python, the PyTorch tensor object 2015, right? So this is an assertion I'm making. Similarly, I'm taking the matrix object, the matrix abstraction that I created using class matrix, and the element at 2015 is the same as the image 2015, as well as the images 2015. This is the PyTorch one, this is the list one, right? And I'm saying that they are all the same, right? So I'm making assertions and the assertions are passed, right? So this is like a kind of a nice unit testing setup with Jupyter notebooks. Similarly, when he takes, he calls this destructuring. Again, you should be quite familiar with for most of us. So you're basically, when you return shape, right? So if you do here, for example, so if I do xtrain shape, so it returns a tuple, right? So this tuple, you can basically deconstruct here implicitly like this, like n and c. So n is the number of rows here, and c is the number of columns here. And then I have these assertions here. Again, I can take this out. So I have these assertions here, which is saying that, n is 50,000, as we have seen, C is 784. And then the minimum in the label set, right? Because we looked at white train as well. And because these are handwritten digits, the only handwritten digits can be from 0 to 9. And so the minimum is 0 and the maximum is 9. So these are, again, a few assertions that we made, and they're passing. Great. So then he goes into another sidebar with random numbers. And I'm not quite sure what the objective is here, but so essentially he goes on to say that these are all pseudo-random, right? So this is from the implementation before Python, used before Python 2.3. And so it uses like two things. It uses the seed, that you can. So if you notice that a lot of reproducible code, you are setting a manual seed in Torch, right? Or in NumPy even, or even in scikit-learn using random state equals something, right? So these are all ways of setting the randomizer to produce a singular sequence, a set of random numbers that are reproducible over multiple calls, right? So the idea here is that, so essentially the random number generators are basically pseudo-random generators, where you set a seed, and maybe this is the point that he's trying to make, that you set a seed and you're able to now reproduce, the randomness, right? So given a random state, if you call, regardless of how many times you call the random number generator, you should get the same kind of things, right? So here, if you see here, here he sets the random seed, and it creates 3 random states, right? And then using these 3 random states, he computes a random number, right? And if you call rand 3 times over time, it gives you 3 different numbers, which is what you expect, right? However, here's the fun part. So if you call rand from 2 different, a parent and a child process, they end up, giving you the exact same number, right? So the idea here is that the random state, as long as the random state doesn't change, right? So you get the exact same number, right? And so here, again, he says, okay, how do you call random? No, actually, this is me, sorry. I actually wanted to see if the same thing you could do in NumPy, right? He does it for the Python thing, and then he goes to Torch, right? So I wanted to basically see how you do it in NumPy. So you replicate this code, and it's again, the behavior is the same, right? And again, no surprises. Tensor Torch again is also the same. Now, if you plot,
if I may, Sujit.
Yeah.
So with respect to context, as to why he kind of dives into this, don't know why he does it at this point, but in the prior FastAI library that he actually created, and potentially I think downstream as he'll create similar libraries, he uses multiprocessing to launch multiple threads
I see, okay.
or multiple processes to parallelize data processing. Now, when he does that, because multiprocessing in Torch, as he's likely to explain, is not, at least in Torch 1.0 or whatever versions, wasn't all that great. So in FastAI library, what he had done was coded his own multiprocessing way of handling data as part of the library. And
okay.
The problem that arose was he had a bug whereby he assumed that when he forked, he was actually getting separate random values, but it turned out that he wasn't. And so he kind of wants to lay the foundation right here that you have to be careful if you're multiprocessing and you're using random.
Okay.
Because if you want to get separate values, if you truly want the 2 threads or the 2 processes to be using different random starting points, you need to be careful about how you go about doing that. That's, I think, the context.
Okay. That totally makes sense. Yeah. Okay. Yeah. Okay. All right. Yeah. Yeah, so most likely, you would, start with multiple seeds, maybe, each thread, right? I'm guessing. Yeah, I don't know. So, anyway. So again, to prove that random actually is random over time, right? So he does this, and as you can see, it's jumping all over the place. And then he takes a larger data set, and then he does a histogram. As you can see, it's mostly a uniform distribution, which again proves that random numbers are all over the place, right? So there is no specific set of random numbers which are more prevalent than the others, right? So that's basically the objective of these two visualizations. And then he also does a time it of how long it takes to do 10 random number calls, right, in this range. And it says 3.91 milliseconds. And then if you do the same thing on torch, it's much faster. It's 56.5 microseconds, right? Okay. So again, he goes back to now this was the sidebar that he went into. So now he's back into matrix multiplication again. So the reason why you want to do matrix multiplication, we just saw how to, but now why, right? Most of neural network stuff involves solving problems like this, right? Linear problems. And basically, here, y is your output variable, your x is your input variable, right? Y is your target variable, sorry. W is the weights and B is the bias, right? So essentially what you're doing here, if your Y is of shape, say, N and C, right? N being the number of records and C being the number of classes. X is of shape, in this case, N and 784. So W would then be of shape because you want NC as output, right? So you would need to have W of shape 784C. So because of the 784 in common in the middle. And then B is of shape because when you do this, X and W, you essentially, when you are multiplying this, you need to be able to add it to the bias here. And we will cover this in broadcasting later on. So, so at this point, to simplify, make a simplifying assumption, let's ignore this, right? So we just talk about Y equals WX. So again, here we want to set the manual seed. We just talked about seed, so you want to make it reproducible, and you declare a weights matrix of size 78410, right? Because we have 10 classes, 0 to 9, right? And your bias is of 10. You will not use the bias at this point, but we have it here. And again, because we know that Python can be quite slow, we basically keep the weights as it is, but for the X part of it, like the WX, it's actually XW here. For the X part of it, we only consider 5 rows, 0 to 5, right? So as you can see, the torch size here is, basically the X part is basically 5784, and the W part is 78410. So we are going to expect 5 by 10 outputs, right? So here we basically deconstruct again, like he showed us. Oh, sorry, I have to take this first. So again, we deconstruct from the shape, right? So this is the A rows, A columns, B rows, B columns, and then this is what you see, the same thing that you saw in shape, right? And now the first draft of matrix multiplication. So essentially, you first take the A rows, A columns, B rows, B columns out of the shape because you're passing in A and B, the two matrices to be multiplied. Then you create a towards zeros, you initialize a holder for this output of A rows and B columns, right? And I think there should be another check here to see if AC and B are the same. If not, it should error out, but they haven't done that here. So we'll just keep it that way. And then you're basically going through each row, I in range, and then you're going through each column, like we saw, right? So each row and each column. And then here you're multiplying the elements and then summing it up into this IJ object, right? So this is like element by element, and you have 1, 2, 3 loops here. And so again, you run the time and you see how long it takes, right? So this is 806 milliseconds. And so you can also just time it just for the heck of it. I decided to draw a graph at the end. So I'm basically capturing the results of the time it and writing it out into this object, which I will use later, right? So this takes a little bit of time because, again, Python, and we are doing 5 times, right? And the -o says like output into this result object, and -n is basically how many times you're doing it, and calculate the mean and standard deviation and so forth. So let's wait for it a bit. Yeah, this is actually not such a great idea, but again, not very surprisingly, we have 810, 801 milliseconds plus or minus 4.06 milliseconds, right? And so again, clearly this is not the best way to do it, right? So then he talks about number, and number has a just-in-time compiler, right? So what happens is that you can declare this .ab, and if you look at this, this is basically the inner loop, right? So if you thought about each row and each column as 2 arrays, the dot basically does element-wise multiplication and sums it up, right? So this is the way in which you would basically do this thing here, right? So if you look at this loop, this is identical, almost identical to this, right? Or analogous, I would say, right? So here the only thing you have to do is basically you have to flip. So instead of you just have to flip the columns, as you'll see here. Inner loop with a call to dot. So because you are transposing one side, and so again, so if you do this, and if you run this the first time, you will see that it takes quite a long time, right? It's 457 milliseconds. But now if you do this, it's 34.3 microseconds. And if you run this multiple times now, you will get something, numbers around this range. So the first time you call it, it needs time to compile into, the C layer, whatever C layer, the number layer, right? And then it just calls the compiled object over and over. So here we have done, matmul, which now uses this dot object, right? This dot definition, sorry, the dot function that we had here. And so essentially now you're able to replace the last loop, right? The last loop from here, this K loop, with this call to dot, right? And so let's see how that works. So if you run this, so you will see that the wall time is much better, right? So it's 80.9 milliseconds compared, and if you run it maybe multiple times, yeah, so you can 587 microseconds, right? And and this is comparable with if you compare it with 801 milliseconds, it's actually quite nice. So similarly, you also do again, and this is like, again, I'm doing this time N50, not N5. And it came back with an average time of 447 microseconds, right? So instead of using dot, right, we could also use something like straight up just element-wise multiplication, right? Dot is basically element-wise multiplication, but in this case, it was like doing it with like this, and now you just flatten it. So here he goes into another little sidebar talking about APL. I will just bring it up. I did not do much with APL here, but he basically talks about how a lot of APL functionality, work to kind of inspired NumPy, and in some cases, yeah, well, a lot of APL basically inspired NumPy, right? NumPy functionality. So there is this little tool here by which you can play with APL and see how it works. And the ideas about broadcasting, for instance, about treating a tensor as a first-class object and so forth, they come from APL, right? So according to Jeremy. So I'm not saying, yeah, okay. So in any case, there is a try appeal here. So so again, if you do this, declare two tensors, 10, 6, and this, and 2, 8, and 7, and if you add them up, you can think of now tensors as almost like, or not almost, as first class objects, which you can add. You can do Boolean operations on, do aggregations on, and you can multiply, and this is element-wise multiplication. So if you see here, if you look at a plus b, so it's 10 plus 2 is 12, 6 plus 8 is 14, minus 4, 7, plus 4, plus 7 is 3, right? Similarly, if you look at the multiplication, 10 times 2 is 20, 6 times 8 is 48, minus 4 times 7 is minus 28. So it's doing element-wise. Here, what you're doing is, if a is less than b, so essentially what it does is 10 less than 2? Is 10 less than 2? No, right? So it's 0. Is 6 less than 8? Yes. So it's 1. And if is minus 4 less than 7? So it's 1. So you get 0, 1, 1. And then you calculate the mean, which is 2/3, right? 0, 1, 1. So, and which is 0.667, right? So, so basically these all check out. And then he goes into another little sidebar on Frobenius norm. And the reason he goes into it is, I think he wants to kind of, think of dot as a special case of Frobenius norm, like basically a norm 1, right? Is it norm 1? Probably not. No, it's not. No, it's not, right? So so in any case, it isn't really applicable here directly, but he kind of talks about it in terms of, do an operation, add everything, and then do another operation, right? So it's kind of like that. So in this case, Frobenius norm is basically take each element, square it, add them up together, and then square root of the square root the sum, right? So essentially, it's square root of the sum of squares, right? Okay. So if you do here, and he goes into Frobenius norm. So essentially, as he mentions, now that we know that matrices are first-class objects, or actually, we just talked about tensors being first-class objects, and here we will see that matrices also, if you do a tensor, which is a two-dimensional tensor in this case, matrices are also first-class objects, and you can do, m star m, which basically does element-wise multiplication, and so you can see what the tensor m is here. Actually, I should have moved this up, maybe. Where is this? One more up. Yeah. So, what is this tensor, right? So 1, 2, 3, 4, 5, 6, whatever. Yeah. And so if I do this, I get, and you can, basically look at it. Oh, I know why it is. I moved it up here. I wanted to see little slices here. So you can also do slicing. I'll leave it up there. That's fine. So, you can look at it here. So if you see, you can also do slicing using this colon notation. Again, not, nothing new for most folks here. So this says, give me the, the 2th row, which is the third row. So in this case, it'd be 7, 8, 9, right? As you can see, 7, 8, 9. And here it's the 2th column, which is the third column, because we are 0 based, right? And again, this is 3, 6, 9, right? So again, nothing probably new here, but this is just for reference. So now using this notation with colons, right, where we can talk about full individual rows, here we are saying that for each I in row and for each I in the left-hand side row, right, and for each j in the right-hand side column, find the row, the entire row, AI, and find the column, the entire column, multiply them, right, and then sum them, right? So you're essentially doing, if you think back to the animation, it's essentially you're doing the same thing, except that you are now doing it in one step, right? So you're doing all of it, and then you're summing it, right? Row, column, and then sum. So we expect it to be a little faster. So let's see how fast it is. So maybe not that fast, because if you look at it from here, we had 801 milliseconds here. And now we are 1.42 milliseconds. Significantly faster, but probably not as, if you compare it with the, the dot here and 457 milliseconds. Okay, maybe, yeah, okay, significantly faster then. Okay. So 1.42 milliseconds. And then, so we also now define another assertion here. We say that, we want to make sure that the numbers that we are generating from each of these matmals, they should be the same. The matrices, the product that we are generating, they should be around the same, right? So for that, we call torch all close, and then we pass in A and B, right? And here, this is the two tolerances. I think row tolerance, and I'm not sure what these is. Actually, it's a good time to actually take a look at it, maybe, right? I missed this. I blindly copied it, so, kind of. So again, something should be, I should be doing. So, so ATOL is absolute tolerance and RTOL is relative tolerance. Not exactly sure what it means, but these are, like, I think, yeah. So
it just differs in the values, right? I mean, if you see the default, the number there, 1E minus 0.8. So you
and 1E
can
minus
see
0.5, yeah.
Yeah. So that's the only thing that differs it between the two numbers, the two floating point numbers that you want to compare. So that's
but I was, how do you actually think of it? This is kind of high level. You're saying that, okay, they should be similar, and these are the kind of guardrails. But exactly what do these guardrails mean? It's not very clear here. Can I, maybe I try going
if you
to
look at the example here, the torch.all close, torch.10 tensor, this is the number, and this is the 1E minus 0.7 is the, I think
I
so,
see.
the
Okay,
absolute,
yeah. Okay.
Maybe you can check the NumPy thing.
Yeah,
for the
I think that
definition.
might, yeah, let's see what that gives us. C notes. Okay, so these are more C notes. Where is the notes? And I think this is what is in RTOL plus abs B, and the absolute difference are added together to compare against the absolute difference between A and B. Ah, I see. Okay. So here he's saying, the absolute value of B, right, plus the RTOL times the RTOL and the absolute difference B, ATOL. So RTOL star abs B plus ATOL is compared against the absolute difference between A and B. So abs of A and B. So probably that's what it is, right? Oh, there it is. Here. Sorry, notes. I think it's also there up in the torch outclose, but more cryptic. So I think this is where the RTOL and ATOL come into play. What the RTOL and ATOL is, right? And I think we saw it here as well. See here, input minus other, right? Here they're calling A and B as input and other. So basically that's what RTOL and ATOL is, right? Okay. So okay. So in here we have actually changed it a little bit because we want slightly higher tolerances. So RTOL is 1E minus 3 and ATOL I think is the default 1E minus 5. And so we create this test close, and then we can assert that T1 and T3 in this case are similar, right? So results that came out are not very different. And so again, I do an time it to store the element-wise numbers from here. And then, so that's what I get here. And as you can see, it's 1.21 milliseconds, which is comparable to the previous one that we saw. Right, so where is this? 1.42 milliseconds. Yeah, so it's kind of similar. Okay. Where are we? I think we did this. Assert no, we didn't actually do this. We defined torch all close here. Yeah. So we are here. So we don't actually have to use our own dot definition, torch. So again, going by the same rules that Jeremy Howard set up. Now that we know how to implement dot, we are allowed to use torch.dot, right? So let's use torch.dot. So again, usage is identical. So, and as you can see, it's 1.14 milliseconds, which seems close enough, I think. Yeah. So this is 1.42, and this is 1.17. So it's slightly faster, right? And then again, we test all close, right? The torch all close thing that we did. So again, we know that T4, which is this one here, is similar, or the numbers are almost identical to T1, right? And as before, we set up some time it numbers to do our graph at the later. And then we talk about broadcasting, right? So so again, there is NumPy documentation. We can go look at it, right? In significantly, detailed, much more detailed than what's written here. So essentially, the idea here is that if you have different size matrices, you can, ordinarily, you would expect NumPy to kind of barf, but in certain cases, NumPy actually, is able to infer what you meant, even though it's not exactly what you said, based on certain rules, right? So these are called broadcasting rules. And so it says, how NumPy treats arrays of different shapes during arithmetic operations. Subject to certain constraints, the smaller array is broadcast across the larger array so that they have compatible shapes. So, and broadcasting provides a means of vectorizing array operations. It's really a convenience, right? So that looping occurs in C instead of Python. And so this is important. So if there was no broadcasting, you would either have to explicitly reshape your arrays so that they fit exactly, or you would have to use for loops, right? So, and using for loops in Python land is actually slower than using it in C land. So therefore, broadcasting does it automatically for you, right? So this is also a speed improvement. It does this without making needless copies of data. Again, if you were to reshape it, or create the broadcasting yourself in your code, you would typically need to make copies of the data, and this one does not need to. Okay, so again, it allows developers to write less code. So it's basically specify how you think instead of explicit. So here again we have two examples: 10, 6, -4, and so if you do, like Boolean operations on it, you get true, true, false. And then he says, but, how was this possible? The right-hand side is a scalar, right? So, and, so essentially the scalar was applied to each element of this vector, right? And you got this, right? So, and so again, you can also do other things with it. You can say, you can do a mean of it, or, other things to it too. So you can do addition, and when you add, as you expect, it will add one more. So your tensor was, where was your tensor? So, okay, this is your tensor. Sorry, so this was your A, right? 10, 6, -4, and you add, it becomes 11, 7, -3. And then you declare another tensor, right? M. And actually, it's the same tensor that you have declared already. And you can do 2*, which is basically applying the 2 to each element and multiplying them each element by 2. Right? So this is broadcasting with a scalar. So essentially, the scalar adapts itself to the size of the vector, the shape of the vector that it's applied to. So now with a matrix, here is another little tidbit he talks about. Basically, there is a language called Yorick, where the idea of broadcasting came to as a scalar. So scalar broadcasting is dates back to APL, but vector, higher rank broadcasting comes from Yorick, and there is a language called Yorick, and there is a user manual here, and this one where it says comes from is basically the Usenet thing where he basically talks about the person who the Yorick creator, I think, talks about this idea, or maybe it's a discussion about this Yorick thing. Okay, so so broadcasting vector to matrix. So we have a so now you have this matrix M, I think, yeah, M, and there is another tensor which is a vector, which is C here, right? And then you want to, and here is M again. And you have, if you look at the shapes, the M shape is 3 by 3, and the C shape is 3, right? So if you do m plus c, so essentially what it is doing, it's basically taking each row of c and adding it to the vector, right? So row wise, right? So you can now see, because 10 plus 1, 20 plus 2, and 30 plus 3 is 11, 22, 33, and so on, right? And this is commutative, so you can do both sides, both ways, and it does the same thing. So again, you can, basically flex your muscle a little bit and say test close, we already wrote it, so let's do it again. But what is actually happening, right? So when you look at C is basically a vector of size, 1, 3, right? And so what internally is happening is it does, expand, C is expanded to the shape of M, right? So expand as, and as you can see, it becomes like 3 row elements. And then of course, when you multiply, you get exactly this. Sorry, if you add to this expanded object, you get exactly the same as you got here. So, but however, as you saw in the NumPy, the snippet that we copied up in the notebook, we don't really copy the rows. It just looks like we did, right? So this is done. If you look at the internal storage, it's given a stride of 0. And so essentially this thing is repeated, right? So, so you can see that the stride, I think, is basically how many things to how many points to jump on the row side and how many points to jump on the column side, right? I'm actually not really sure of this. We could basically look at what the stride means. Let's see really quickly. The expanders, right? So okay, and then it says tensor and then tensor stride. So it says stride is the jump necessary to go from one element to the next one in the specified dimension dim, right? So if you have stride 5, 1, so essentially what he's saying is that every 5, so in the first dimension, so if you think of this, right? So x stride 0 is 5.
The way,
yeah.
Sujit, if you are going in the row dimension, you need to skip 5 numbers to get from 1 to 6.
Okay.
If you're going in the column dimension, then you need to skip 1 number to go from 1 to 2.
I see. So okay, going from here to here. Okay. Okay, got it.
Yeah,
okay.
And the dimension is 0 for rows and 1 for column, right? So if you say x dot stride 0, which is along the rows, then you'll need to jump 6 when you have 5 elements rows.
I see. Okay.
So if you have 3 element rows, then if you're going to the next element along the row, you need to skip 3, right? 1, 2, 3, 4. So you skip to the next element along the row dimension, then you need to skip 4.
Right.
But if you go along the column dimension, then you need to skip just 1.
Yeah, and I think the 0 is because you're not actually going anywhere. You're coming back here, right? Because with the expanders, you're not internally. You just have this. So essentially, when you go to the next logical next step, you're basically coming back to the same place.
Yes.
Right. Yeah. Okay. Yeah, that makes sense. And 1 is basically because you go to the next element. In this case, it's a full element. Right. Okay. Cool. Very nice. So okay, thank you. This is good. I understand now a little bit. Okay. So there is also another thing he talks about where he oftentimes you might need to add an extra dummy index, right? So to do that, we can do either unsqueeze, where you basically take, so for example, if you have C, this, we already know what C is here, right? Where is C? Here, it's a tensor of 10, 20, 30, right? And let's assume that we want to add another dimension along the top axis, right? So, and if you do, you can do it in multiple ways. One of them is doing C dot unsqueeze dimension 0, which adds a dimension at the, the beginning of your thing. So it used to be like a, 3 dimensional thing, right? So now it's like a 1, 3, right? So yeah. And now you can add a none here, and you can do this. Or there is also another way where you can do new axis. I think NumPy has new axis. I'm not sure if Torch has new axis, right? But these are both supported in Torch, right? So if you look, this is what happens. From we had this used to be what C was, right? The tensor of this. Now, because of the unsqueeze, you have an additional dimension which it's embedded in, and it's the same with the none, right? So, okay. And then, as you can see here, C dot shape used to be 3, and now it's 1, 3. It's basically, exactly what we just saw earlier. So similarly, you can add an index along the column, right? So instead of having an index on the row, you can say unsqueeze. Typically, you would say unsqueeze -1, which is the last element, right? In this case, because there are just 2, you don't really care. So if you do unsqueeze here, on the first column, or you can move, you can, put none on the last element, right? So you can do this, and you see exactly, it's now a transpose of this, right? So, and if you do the shape, so it used to be like a column of size 3, right? It's a vector of 3 rows, right? And now it's basically 3, 1, right? So you have added an additional dimension at the end. So, okay.
Unsqueeze only works in Python, right?
Unsqueeze, I think, no, unsqueeze works in PyTorch. I don't think it, I've seen squeeze, NP, NP unsqueeze. I don't think it works in NumPy. Yeah, expand dims. NP doesn't have, NumPy doesn't have unsqueeze, but Torch does. Yeah, and NP you would typically use expand dims or new axis. New axis I think works on NumPy. Yeah.
Okay.
Okay. So and then, okay. So here he adds 2 other things. So, trailing colons, where you say, okay, 3, colon, right, is basically the same as 3, right? So if you say, if you have a matrix and you say M 3, colon, you basically, you're saying, give me the 4th row of this matrix, right? 2-dimensional matrix. But you can also just say M3 and it will be in the same thing, right? So that's what he's saying here. Skip trailing colons. And similarly, this is more esoteric, I think. Most people don't use it. But you can also use ... to mean all preceding dimensions, right? So, you can basically see this. And, if you do this, you can see how it expands the 10, 20, 30 now in column format rather than row format. So now if you multiply or if you add to M, it adds like differently, right? It adds column by column. And similarly, it's commutative. We know that, right? And okay, so now he's kind of formalizing the broadcasting rules. And, it says basically, so it starts with the trailing dimensions, how broadcasting works, and it works its way forward. So 2 dimensions are compatible when they're equal, obviously, or one of them is 1, right? In which case the dimension is broadcast to make it the same size, right? So this we saw in the scalar case, right? Also, if you have things like, and so this is in scalars, it's obvious, right? It's, this is always 1. But now in this case, for example, so let's say you want to scale an array, multiply by, actually this is also the same thing, so it becomes 1 by 1 by 3. But even if you have like 2, right, and it will just add 1 to make it all equal, right? So if you saw the bias thing, right, where we were saying we want to do 1 comma c, right? So essentially, sorry, it's c comma 1, I think, right? Anyway, so that's basically the broadcasting rules here, right? I'm just going to kind of, and there are more examples here, which probably is, gives you much more insight. So if you look at, for example, here, so it says, so here it says, 8 by 1 by 6 by 1, and you have 7 by 1 here, and by 5. So the ones all get subsumed, right? So you basically see this 1 and 5 becomes 5, broadcast to 5, 6 and 1 broadcast to 6, 7 and 1 broadcast to 7, and 8 is implicitly, this is 1, so 8 get broadcast, right? So similarly, there are various examples here, and you can go through them and kind of get more clarity about what broadcasting means. So, okay, so again, there are some more examples here, and you say, okay, going back to our own example here. So we want to multiply a row of M1 with M2. So M1 0 will give you like 784, and so this we add like an additional, so this is like 784 rows and 1 column now, right? Because we added an axis here, and we have M2, which is shape 784 by 10, right? So essentially we now want to multiply a 784 by 1 with 784 by 10, right? So M1 is LHS and M2 is RHS. So how does that work? We basically say that we have 784 by 1 and 784 by 10. So because it's 1, it gets broadcast to 10, right? So now they are the same shape, and now we are able to do element-wise multiplication, and the product is 784 by 10, right? Okay. And again, just to make sure or kind of be explicit about what's happening here, if you do an LHS expanded RHS, you will see it actually does exactly the same thing. It takes the 1, makes it to a 10, right?
We replaced it here. If you could scroll a bit upwards,
mm-hmm.
yeah, we replaced it here. The LHS was replaced with row 1, 9.
Yes.
Yes.
So this is M1 0.
Okay.
Right. So it's because M1 is like 5 by 784. We are just taking 1. We just want to take 1 row, right?
Okay.
Yeah.
Okay.
And so yeah, it gets confusing here. So just to keep myself honest and to make kind of be more explicit about it, I took the LHS shape, whatever LHS was created, right, after adding this, taking the 0th element and then adding the extra dimension at the end. I explicitly set it out here, so that's why you can kind of see it here. It's much more easy to read at this point.
Cool.
So
thanks.
So the idea here is that we are going to basically take our multiplication, and we are going to do like a column of A, right? So for each row of A, we are going to take the column, right? So for each row of A, right? We are going to take the row. We are going to add this extra. So this is exactly the same thing we did here, right? We took the row and added a none here. So, and row is basically M1 0. So here we are doing AI, M1I, and adding, and basically saying that, add an extra element here and then multiply by B. So if you do that, then, so essentially at that point, this thing becomes a 784 by 1, right? And this thing becomes a 784 by 10. Because this was already, B is the M2, right? So let's see, where is it?
Yeah, this is where, sorry to interrupt, Sujit, actually, this one threw me for a loop until I figured out that B is actually the full matrix.
Yes.
And you convert it into a column and multiply through the matrix, and that's how you get the results.
Right.
Initially, I was confused, and it's an element-wise multiplication, so you can do that.
Yeah.
But B here is the full matrix, not a row, not a column.
Right. Right. Yeah. Here, the left-hand side, you're doing row-wise only, right? But you're multiplying the each row against the full right-hand side weight matrix.
Yeah. So you convert it. The first A I, colon, none. What it does is it takes the row of the A matrix, converts it to a column vector. So it converts from a row vector to a column vector, and then multiplies throughout the B matrix, and then sums along the row dimension in order to get the elements.
Yeah.
That what I would suggest people do, because until I did it, at least it was still confusing for me, is to take very small A and B matrices like you had of 2 by 3 or 2 by 2 and then 2 by 3, and actually do the thing with indices to figure out what's actually going on there. Because if you try it with 784, it's so huge that you don't understand.
Good point. I mean, this is actually the fact that the weight matrix is the full matrix, and that you're applying this thing row-wise across it, right? So
and the star here is an element-wise.
Element-wise, yes.
Not because he's done so many variations, right? A dot, on the other hand, is a complete multiplication of all of the elements. In this case, it's a column vector multiplied by the entire matrix, and then summed along the row.
Yeah, it's exactly this thing here. It's this thing here, just applied, on the entire thing. Well, here also it's the entire thing. It's like 784 by 10, but yeah. So I think you can get some insight from this, right? This breakout, and then but definitely that's a really good point, that you're using the entire matrix on the right hand side. So anyway, so if you run this, you get about 424 microseconds, which is quite fast, right? And then just to make sure that we haven't messed up anything, we do an assert, right? And then so this is for broadcasting. So we capture the times here. And then we go to Einstein summation, which is high level and easier to understand, really. I mean, if you just get past the notation. So here again, we have the M1 and M2. The M1 is 5 rows of 784 elements each. And the weight matrix is 784 by 10, right? That projects it into 10 classes, right? And so if you do an einsum, you're basically saying that I and K, right? So the left-hand side matrix, you're representing by the array indices of I and K, and the right-hand side, you're saying they're K and J, right? And you're saying that you give me a matrix which is 3-dimensional now, like which has all 3 dimensions, right? So which basically says that so you say IKJ. The reason we have this is not truly matrix multiplication. Matrix multiplication is this, right? IKKJ goes to IJ. But the reason Jeremy Howard basically shows this is that einsum says that it's a compact representation, products and combined product and sum in general way. And key rules are repeating letters between input arrays means the values along the axis will be multiplied together. And omitting a letter from the output means the values along that axis will be summed. So the point here is that you do not, even though it's called line sum, and then there is a a thing about being summed, you don't actually have to do the sum, right? You can basically just use it for matrix multiplication straight off, right? So that's what we'll do here. And as you can see, you get 5 by 784 by 10, like it's a rank 3 matrix. And then you can now sum along the first axis, the dimension 1, right? and that gives you like 5 by 10, right? And you can just skip these 2 steps and just make it into 1, and you can basically do the same thing by omitting the k in from here, right? Which does implicitly would sum it now. Now, based on that, let's see how fast that is, right? So we do this and we get 171 microseconds. Again, just to keep ourselves honest, to make sure we haven't, messed up anywhere. And then, I just keep it here. So now I want to show you the little graph that I had. So, these results got captured into these 3 tuples here, right? So Python number, element wise, and then I basically run this. And as you can see, einsum is like by far the best method. Torch dot does reasonably well. So does element wise about the same. Broadcasting does better than this, right? And of course, Python is the worst, right? So which is not totally unexpected. I was kind of surprised about the einsum part. I thought that other methods would have more, but einsum actually uses torch internal, so most likely it is the best here. So now that we know that we can work with small slices, and we are safe that we have at least one method which is really good and which we can apply to the entire all 50,000 rather than just the 5 rows. Let's do it, right? So so we take the entire xtrain and we want to now do a matmul. So the matmul is the last definition here, which is the einsum, right? This is the matmul that we are using now because we have redefined it constantly. So here we want to see what the output of matmul looks like. And so to do that, we don't want to make it too cluttered. So I've just used this precision here. This is another of Jeremy Howard's things where he sets these global variables and display variables, which is quite convenient actually. So if you look, it comes back almost instantaneously, 43.1 milliseconds, and it gives you this the full matrix, right? So we can now do a time it and basically see how long it takes. It's 4.99 milliseconds. Not bad. Okay. Now that we know how to do matmul, right, using einsum, well, we already know how to do it now. So let's try doing other things that we can do, right? So instead of having our own matmul, we can actually just use the at operator. So PyTorch has an at operator. It also has a matmul operator, which we will use here below. And you can see that it does exactly the same thing, creates very similar results. And then, it does 4.74 milliseconds, which is not bad. If you compare it with 43.1 milliseconds, it's better than the matmul, right? Okay. We can also do torch matmul, which again, similar results. And then 4.5 milliseconds, which is kind of the same, right? And again, as you would expect, right? So now he goes to CUDA, and this is why I needed to have the GPU set, right? And so here, so the idea of CUDA is that you have a grid of many parallel processing units, right? And each of them do something very small. So if you think about computer graphics, this allows you to take a frame and do operations on each pixel in the frame, right? So, and it's the same with we neural networks kind of took that and use that functionality to basically do parallel operations on batches of data, right? So here, because we are doing matrix, and for matrix multiplication, the idea is the same. It's basically a 2D kind of thing, right? So like an image, basically you can apply it and then have all the pixels or all the elements be attached, or operated on at once, right? So here our matmul, which is the CUDA, friendly matmul, if you will, has an additional thing that you need to pass in, which is the grid. What is the part of the frame that you're operating on, right? So this essentially will run matmul in parallel on all these little frames on the on the big matrix, right? And then you have A and B, which are the ones that you already know about, and you have a C, which is the holder, right? So what happens, what is the output of A and B, and where do you put it, right? So here, for example, if you take this grid, everything is the same except that it's operating only on just the elements of the grid, right? I and j. So it's bound by I and j here. So if you look, it says if I is less than C dot shape 0 is like the seashells on the seashells, yeah, whatever. And j is less than 1, so it's bounded in that array given by the grid. Apply this transformation, right? This is a familiar transformation, right? So, you're basically saying that, aik times bkj, you multiply and add, right? Each element of the row, each element of the column, except that these are really small. This is not the entire matrix. This is just a part of the matrix. So you do this, and here we are saying that our grid is just 0, 0, right? So the first element we want to operate on. And if you see, and if you remember, it used to be, well, not here. So, okay. So it works out to 10.94. I think I saw it somewhere else. But anyway, so it just operates in the first element here, right? So, and everything else is blank because we didn't ask it to do anything else. Now, we can, we can now apply to, if you think of this grid as being individual elements, we can now apply this thing to all the grid elements, right? We are not doing it in parallel, but we are basically applying this kernel for each I and j, right? We are composing the grid, right? So if I in range grid x, and in our case, the entire grid is, where is this grid x? ARBC, right? So this entire, this thing here, right, corresponds to this thing here, right? So, so you're passing in the grid elements, and then you're calling the kernel that we had here, right? So the kernel is basically, the reference to the kernel is the matmul here. It's a function being passed in. And here we are saying that what are the arguments to this kernel function that you had, right? So these are our own arguments to this function. And then we say star args, which is, additional functions which will get picked up here internally, right? So what we have done here is that, if you remember, so matmul is being passed in as the kernel. So you're saying kernel, which is matmul, and you're saying here is our grid, and this is each individual element, so 0, 0, 0, 1, 0, 2, and so on. And the args that you passed in here are ARBC, right? M1, M2, I think. ARBC, wait. Towards zeros, so ARBC. Grid X, grid Y. Oh, this is the full grid, I think. So these two are the grid X and grid Y, right? And these are the args that will get fed in, as you can see here, that gets fed in here with the, and keyword args are actually not needed here. These would be correspond to anything which you pass in through positional parameters. So basically, if you call this, you will see that this gets applied. It takes a little bit of time, but it gets applied to all the elements, right? The same, the matmul function that we had gets applied to all the elements. And so this is the idea behind CUDA. Obviously, this is still not CUDA. So now we take this same thing, right? Same idea. And now, we take the same matmul idea here, and we basically do it on CUDA, right? So for this, you import CUDA from number, and you have this annotation, which is CUDA.jet. And then you define here A, B, and C. You don't pass the grid in here. CUDA basically has its own grid object, which it passes in. So you take the, ij that you have, right? And you say this is a grid of rank 2, right? So you get I and j. And then for each, the patch defined by I and j, you apply this, aik times p, and you sum it up and so forth, right? So if you run this, and you'll see that it runs here. So this is, I don't actually have a time, so I'm guessing it works the similar way as the JIT thing in before. And here he has some boilerplate that you have to pass in. when you do, first off, you have to basically pass in all these. Okay, here is the other thing. So each of these things, or each of the elements A, B, C that you had, the results, the results that you declared, the NP zeros, and also the M1 and M2, they need to be put on the GPU, right? So basically, you do CUDA to device, which is the GPU, and again you use the map here, and this applies to each of the training weights and R, right? X-train, weights, and R, all three, right? And you take that and you apply CUDA to device to each of these things. So this basically goes on the GPU. And now if you look at the shape, you already know what the shape is, but so this actually, I should have put it out into a separate, let me actually do that while there is time, while I remember. Right. So we put that in on the GPU. Now here is some boilerplate. So this is threads per block with 16. This is really something that you need to pass in as a high-level parameter to. This is for the GPU to work. So he doesn't really go into very much detail on this, but this is mainly for boilerplate. And again, you will never use it in real life because you will be using Torch GPU things, but this is only for illustration purposes. So you have to pass this blocks per grade and TPB to your matmul, right? The matmul that you had earlier. And then you have these elements, the A, the B, and the C, right? But these are all on GPU now. If you see M1G, M2G, and R2G. And at the end of it, whatever comes out, you are basically passing it into R, right? The RG. Now RG has to be copied back to CPU land, right? So you basically say copy to host, RG.copy to host. So if you do that, again, we want to see if we messed up anywhere. So again, if you do a tensor, dtype. So I do that torch.float again. So just to make sure it's R is actually a tensor object. And then I compare it with TR, and it doesn't complain, right? So it's, and then this time I want to do full results. I want to do another graph where I can compare the results here. So this is for CUDA, and if you use so if you want to use torch operation, right, on CUDA, so essentially you're saying that you're passing in the X-train to CUDA and you're passing in the weights to CUDA, and then you're taking R, you're computing R, but basically you're using torch at operator here to do the multiplication, and then you're passing it back to CPU, right? So to do that, it takes 1.02 seconds. If you do a time it, we will save it up. So 871 microseconds, which is quite good. So again, we compared the results, and in between einsum, torch, and these are all the full multiplications, right? And as you can see here, torch at on CUDA is really fast. CUDA is the next best. Torch matmul on CPU, torch at on CPU, almost comparable. Einsum, a little higher, but again comparable. So that's the end of. I'm actually 9:38, so I think we did 1.5 hours. Okay, so we have time. So yeah, so that was the end of my spiel.
Yeah, the CUDA thing was a bit tricky.
Yes.
Yeah, with respect to applications. I don't think so. People use this very much in their kernels. But if I talk about flash extension and such transformers which have those CUDA kernels, which in those multi-attention heads, which are used in nowadays the LLM trainings. So flash attention, just to the site for those who do not know, has a CUDA kernel too. fused CUDA kernel too. So I was thinking fuse CUDA kernel with the Python implementation. So what they do is they have a Python implementation of a particular eigensum, like an eigensum, and they also provide a fused CUDA kernel with the same set of dimensions. And what they do is that makes their whole operation 2 to 3 times faster.
Oh,
That
okay.
particular group, particular group of operations. So I was thinking of applying it there, and how people might have gone there to apply it in their respective transformers, those LLMs that are being trained.
But wouldn't it make sense to just use the PyTorch numerical algebra stuff? I mean, is there any reason why you would use number?
No, they do not use number. They combine the PyTorch,
Okay.
the native PyTorch with the PyTorch CUDA.
Okay.
So
that makes sense. Okay.
So they fused it
Mhm.
with the native PyTorch and PyTorch CUDA. They fused the left and the right hand side together, and they formed a group of a continuous mapping function or iterative mapping function that has a JIT compilation, which can be used to accelerate the whole LLM training process.
Okay. Cool. Yeah. My battery is like reporting low, so I'll be back in like a few minutes. Okay, I'll just get my power cord.
Yeah, the tuning in CUDA is specific, obviously, to when you're down. The reason he needs to do the threads and the threads per block and the blocks per grid and stuff is usually all that is hidden behind CUDA, which NVIDIA takes care of depending on the architecture, because as the architecture varies, the number of threads per block and the blocks per grid and stuff would vary. But that's all hidden typically at or within the CUDA layer, and everything operates like Torch typically operates on top of that, and so you don't see that. But if you want even more fine tuning, then obviously you go down close to the metal. And when you do, then you get exposed to things like how many grids are there per block and how many threads can you launch, and what's the best performance you get. And while you get nowhere near to what CUDA gives you or the GPUs as in graphic processors give you, the CPUs also have parallelization in vector processing, and that helps you as well somewhat. So the extent to which you want to optimize these things depends on the effort you put in and how close to the hardware you get as you try to tweak your algorithms.
Yeah, true.
And some of the linear algebra matrix multiplications of huge matrices are coded. There are a whole series of BLAST algorithms, which a lot of the genomics and proteomics guys use. And amazingly, for a very long time, they were coded in Fortran. And Fortran was very close to the hardware.
There is a completely off-topic thing that I saw some time back. There is Alpha Tensor. So it's basically the AlphaGo people, AlphaFold, AlphaGo, the same family of RL techniques, right? So they're using RL to speed up matrix multiplication. So the idea is that for different ranks, different combinations of ranks even, there exist in shortcuts, decomposition shortcuts in the matrix multiplication space. So they basically use alpha tensor to discover that. So I thought it was, again, it's like super off topic, but since we're talking about matrix multiplication. Right?
Yeah, no, I think if you really want to get into the nuances of matrix multiplication and understand it at the next level, way back, there was a link provided to, in fact, a course that Fast AI.
Oh yeah, chapter 4, somewhere here. Yeah.
Right, on numerical algebra. And I would, if you want to get to the next level of detail on how to execute these matrix, how these matrix multiplication algorithms are coded, and the variety of optimizations that are possible, which would eventually lead to things like what Sujit is talking about, then this course is really good. And of course, there are multiple college courses as well, but this one has the videos and the notebooks that go along with it, and how you can speed up the various implementations of matrix multiplication. And goes through, I forget the name of the lecture she goes through.
It's here. I put it up here. It's this one, computational linear algebra coders.
Right. Yeah, that's a really good course. Rachel Thomas goes through that, and
this looks
really
nice.
Good
I mean,
if you're interested in the next level of detail, especially the simple things like SVD and your factorization. And
I will check it out. It put it on my queue basically.
Yeah, but very soon you find out that that's extremely specialized.
Right. Yeah.
People have spent careers optimizing single particular snippets of code which underlie so much infrastructure that.
Yeah, but I think what I'm more after is like insights. I see some people I work with, right? They basically have these almost magical insights into numbers, matrices, right? They look at like a thing and say, oh, you can maybe decompose it along this line, right? So this was almost like recommendation systems, right? So you have recommendations, and you can take the customers and the products, and you can decompose them into two things, right? So this was the particular example I'm thinking of is in terms of knowledge graphs, to find links between entities that were not there, discover new links basically. So we use matrix factorization for that. And the whole the idea that that you can sort of do that, I thought that was at least when I first heard it, I thought it was magical. But I think this kind of this kind of course might help give you that kind of insight. Maybe not the high level, deep understanding of numbers or mathematics or whatever, but just the insights from if you almost like
the math is actually fairly simple. It's like you say, the ability to kind of, but for that, the best course, if you have the time to really build up the intuition and understand what's going on, is the Gilbert-Strang course.
Okay. Yeah.
If you really want insight into matrices and linear algebra, then that's the best course.
Okay.
This one focuses more on the implementation of the algorithm. Gilbert-Strang's course, if you can plug through it and have the time for it, is the thing that really builds up from the foundations again and gives you a very strong intuition of what it is that you're trying to do with all these operations. So it not only gives you the math,
Okay.
it gives you kind of
Why?
the
Yeah.
why.
Okay.
And, you know, over time you lose it and you have to go back to it, but that's the best. Any questions or comments? Any additional questions or comments? Thanks a lot, Sujit. Appreciate you taking us through the whole thing and look forward to the next lecture. Thanks everybody for joining.
All right. Thank you. Yeah.
See you all next week.
Right. Bye.
Thanks everyone. Take care.
Bye.
Thank you.
Thank you. Bye.